We can move to the final talk of today. Eduard, please.
Share the screen. Do you see the screen?
We can see the screen, we can see your mouse, and we
Okay,
can
good.
hear you. It's
Okay,
all yours.
All right, thank you. So today I will give a brief introduction into ngFEOSAD code, which I developed with colleagues of mine, a few colleagues here. And it's a three-dimensional gas-dust hydrodynamics code, and it's particularly useful for simulating the very early stages of star and planet formation. I was always fascinated with this transition, you know, from a big cloud, which is tens of thousands, yeah, 220,000, yeah, astronomical units, something like that, and how it transits into a protostar and a protoplanetary disk, which is much smaller in size. And this is the challenge of this sort of simulations. So what, for instance, Sergey has shown with gFargo, or with Fargo and the clones, basically they consider isolated disks. And if they want to see the effect of this transition, they impose some inflow rate onto the disk. There are prescriptions to do that. But this is not self-consistent, of course. But self-consistent, just consider cloud, rotating cloud, and see how it collapses to form a star in a disk. And there are codes that can do that in Japan. And also here in Europe, they use, usually for these purposes, they use spherical coordinates. But with the spherical coordinates, there is a significant problem with the coordinate singularity. We have a coordinate singularity in the center and along the axis. And that is difficult to handle. And usually people just introduce a sinc cell, spherical sinc cell there. But that also introduces a problem with the inner boundary. What we decided to do, we just decided to use Cartesian coordinates and nested meshes. And this is an example of that. And in Fortran, there is this feature, coarray. If you're familiar with Fortran, this is a recent feature. Coarrays, they basically, it's a sort of MPI. It's a simple MPI. You know, with MPI, it's difficult to code with MPI because you have to really know this all intricacies of parallel programming. With coarray, it's much easier. I've learned it during 1 week, and that's it. And I started coding. And coarray extends you to multiple nodes. So you're not anymore using one single node. You can use several nodes. And each of these are nested meshes. They can be one coarray in Fortran, and they just communicate with each other. So it's very handy way to do parallelization. Now we can simulate from larger scales, thousands of AU down to the disk, protostar, formation of protostar disk. And the typical number of nested grids here is up to 12 I have tested. With 12 nested grids, I can get to resolution 0.1 of astronomical unit. And these are, at the moment, equations that are solved. The standard continuity equation and momentum equations. It's a polytropic approximation at the moment. And there are two, in addition, there are two populations of dust. Small dust, smaller than 1 micron, and grown dust, which you call grown, bigger than 1 micron. This transition is artificial, can be set to any value. And small dust is linked strictly to gas, and grown dust has it has an additional equation, dynamical equation. We have self-gravity, drag between the two, and also conversion of small dust into grown as the dust size, maximum dust size increases. The gas is solved by the Godunov method, which HLLC Riemann solver. Dust is also sort of Godunov method, but it's a pressureless fluid. The advection is we use the third order piecewise parabolic advection, which allows us to conserve relatively good angular momentum. Second order scheme didn't work well. We switched to third order scheme. And dust to gas friction, we either use fully implicit scheme or semi-analytic integration. Now we use a simplified monodispersed dust grown model motivated by Binstiel 2012. We solve this equation where A max is the maximum size of dust grains, and dust growth due to because of neutral collisions, and the relative velocity is that of the turbulent. So it's related to alpha risk, which is a parameter in our model, and the Stokes number, the sound speed. And dust can grow until it just reaches the fragmentation barrier, and then the growth is stopped. We start with a dust spectrum. There's a small dust. It has a spectrum from 5 submicron to 2 micron, and then this stays fixed, but this number 2 micron, it can increase depending on the solution, this equation, also on advection of A max with fluid. And the dust slope is fixed, usually is minus 3.5, but it can be, any way it can be chosen. We start with a Bonner-Ebert sphere. It's something in between the shoe, this single isothermal sphere profile, and the Larsen-Penston profile here. And the red line is a Bonner-Ebert sphere. And we give it some rotation and a positive perturbation, about 20–30% in perturbation to density, so that cloud starts collapsing. We also, how do we do with the central star? So we can either simulate without introducing a sink particle as a central star. And if you want to really see what's forming in the center, resolve that protostar. Or if you want actually to see the disk, how disk evolves, you have to introduce a sink particle. So it's not a sink cell. So it's not like a sphere which we introduce inside and it's empty inside. That's what they do in spherical coordinates. It's empty. But fluid is still going. I mean, we solve the fluid dynamics equations over the entire grid here. But if the density in a sphere here, we call it sink sphere, about 1 astronomical unit, if the density exceeds a certain threshold, usually taken like 10 to the 13 particles cube, then we start extracting this extra density from the sphere according to this equation, proportional to the orbital angular velocity here, and also applying some smoothing function. And we extract that density and put it into the central star. And also the dust is also extracted accordingly. Momentum of gas and dust are also adjusted accordingly. And then this is the sort of accretion rate we get with the sink. But I also introduced a stellar motion. So the sink, the star here is not nailed down to the coordinate center. It can move in response to the forming disk. And here you see it's a radial distance from the coordinate center, how it just moves around. And it actually turned out important because it can significantly alter the disk evolution. So this is animation I show you of the disk formation. here is motionless star, and this column, right, is with stellar motion. And you see this, it's a absolutely identical setup, initial setup. And you see that if we have a motionless star, then the disk develops a strong one-arm spiral time after time. But the simulation of a disk with stellar motion, it lacks this feature. We still, it remains to be understood why this motionless star produces this one-arm spiral. But of course, this is more realistic case. And in the end, you can see that the disk, this is the gas, this is cut through the midplane and through the density, gas density distribution, and dust. From dust distribution, you see that dust has grown already to millimeters at least, and we see the rings start forming in the very inner parts of the dust rings. Here, another view on the disk, again, gas, dust, and now I also show the vertical cuts. You can see that how the disk looks at the edge, basically if you viewed edge on. And one of interesting applications that we now develop with this code, we take the data from our 3D simulations and put it to the RADAM 3D code developed by Dulimond and collaborators. And we then, from RADAM 3D, we obtain radiation fluxes at certain wavelengths. Usually it's band 6, ALMA band 6. We get these radiation fluxes corresponding to our disks, and then deport them into ALMA observation support tool. And from there, we already get realistic fluxes of our model disk. And then we apply the methods that observers use to estimate disk radii and masses, and compare that with our true disk masses and radii. So first, we consider our model disk and apply conditions from JUICE 2012, which are very often used to outline the disk outer edge. So the black region is not empty, it's filled with rarefied envelope, but we have to cut out that envelope. So the disk, separate the disk from the envelope. We use these conditions so that rotational velocity have to be twice the radial infall velocity, twice the vertical infall velocity from top and bottom. This is midplane. And the disk has to be rotationally supported and density above certain threshold. So you see how well we can cut out the disk now. And it turns out that the radius, the average radius of this disk is about 553 astronomical units. And the dust mass is about 670 Earth masses. And now we do our exercise with RADAMS and ALMA OST tool. We take band 6, 1 hour integration on source, and the beam size as shown here. And what you see here are different images for different distances. So each column is a different distance to the source. And each row is the different maximum size of dust grains. So we artificially limit the maximum dust size here in the first row to 10 microns, here to 100 microns, and here to 1 millimeter. And what you see, and you pay attention to these circles. The inner circle outlines the radial distance within which 90% of the flux is. Total flux at 0.3 millimeters at band 6, basically, is confined. And the outer circle is when 97% of the flux is confined. Why is this value? This is what observers usually use, some plus minus 90, 95, 97. What do we see? If we go from smaller distances to larger distances, then the apparent size of the disk increases. The same happens as we go from smaller dust grains to larger dust grains. The apparent size of the disk increases. And the variations turn out to be quite substantial around the true value of 53 astronomical units. It's from 29 to 84. So it means the same disk observed at different evolution stages read different dust size, maximum dust size, or the same disk observed at different distances will have different radii. Why is that happening? This slide shows the reason. So the why it happens. So here we show the radiation intensity. Radiation intensity of our disks azimuthally average as a function of distance. And for different distances to the source and for different maximum sizes of dust grains. So pay attention first to these two. So what is the upper two curves here? These are curves for small dust, 10 micron, 100 micron. And as the dust becomes greater, approaches 1 micron, then the profile becomes shallower. This happens because the dust becomes optically thick at this dust size. It's optically thin here, and then mostly optically thin, and then it becomes optically thick at 1 millimeter. And in optically thin case, the intensity is proportional to the Planck function times optical depth, and both decline with distance, so it's steeper. But in the optically thick case, it becomes proportional only to the Planck function, so it becomes shallow. And as we go from 140 parsecs to larger distances, we also see that all profiles become shallow. And this is effect of beam smearing, become shallower and shallower. So that's, we also plan to include line modeling, molecular line modeling to see how, what we can get out of that. But it's already interesting to see that the same disk can look just quite different depending on the stage of dust growth and distance to the source. And finally, I showed this slide. We can also simulate pebbles. It's a spatial distribution at very early stages and total mass. And one of our results was that pebbles, at this very early stages, they already exist. In a disk of 17 kiloyear, we already have several tens of Earth masses of pebbles. However, their spatial distribution is very patchy. There are regions where pebbles exist, and they're interchange with regions where they're missing. How we determine pebbles? We determine these dust grains. They should be greater than 0.5 millimeter, and the stalks should be greater than 1 in 100. So when we scan our disk, we see that pebbles are there. This is midplane, the vertical cut, they're in the midplane, but their distribution is quite patchy. So to conclude the talk, the key features of ngFEOSAD, I think there are many codes, not many, but there are a few codes that you can use to do similar things, and they may be even more advanced. But one particularly attractive feature of ngFEOSAD, it's not really computation expensive. So you just need a small institutional cluster. If you have 3 nodes with 48 cores, you can start running it. Usually for these fancy codes, you need tens, not hundreds of computer nodes. And it's difficult to get that time. But with ngFEOSAD, can get some results already with very limited institutional facilities. And we have this interface, direct interface with Radom 3D. We can port their density, gas density, and dust density distribution, including dust sizes. So we can see if the dust size varies. We develop that interface. You can port that and produce images, realistic images, and can try to interpret the observations with this tool. And I hope that in the near future, I will include radiating transfer. It's almost done, but I have problems with boundaries. I have to solve that at the interface between the nested grids, something goes wrong there. And in some, I don't know, maybe a couple of years future, maybe we'll include magnetic fields. Thank you very much.
Thank you very much for this very, very interesting presentation. I already have the first question. So is the code publicly available? Do we have to contact you? Can we use the code?
It will be publicly available within several months, but now I can share it with anybody.
Oh, fantastic.
Yeah, I can share that with anybody, and it will be publicly available because this is a paid project by Austrian. I got this grant, and by conditions of the grant, I must make it publicly available, so it will be publicly available.
Oh, fantastic. We have a question. Liz, please.
Yes, thank you. Thank you for the talk. Is it possible to form several stars?
Technically, yes. We have developed in such way that, yeah, we can just put a parameter, how many we can make, and yes, it may take a little bit of more modification because we have to include still the interaction between the objects. So each object will interact, but not with each other. But it's a small modification. It's not difficult to do. But with this motion, yeah, it's now with motion on the side. It took a lot of time really to implement it properly because the star tended to fly away something, but now it works.
Okay, thank you. That's very cool.
Yeah, I have another follow-up question. Maybe you said it and I missed it. So, I mean, one of the advantages, of course, if you use cylindrical coordinates, you, of course, have less problem with angular momentum.
Cartesian.
Yeah, but you're using Cartesian coordinates. So could you expand a little bit about angular momentum conservation in these type of simulations?
Well, it's a known problem that it's better for angular momentum to use conservation to use spherical coordinates when motion is perpendicular to occurs perpendicular to the coordinate surfaces, right? But here, yeah, so basically, you should see already that the non-conservation of angular momentum from what you get. If it's non-conserved, the disk becomes very spread and something like not correct happening to it. But we check the global conservation. Yeah, the global conservation is pretty good. It's maybe the loss of really much smaller than 1%, much smaller. So it doesn't really affect the simulation. Of course, the angular momentum is locally fully conserved, but globally, yeah, there's still some leakage, but it's very, very small. The mass is absolutely conserved, of course. The angular momentum, because of this problem of Cartesian, when the flow is not perpendicular to the coordinates, most always not perpendicular to coordinate surfaces. But what we have seen that if we use a second order accurate advection scheme like one layer, then then the leakage is huge. So that's why we developed a piecewise parabolic scheme, third order accurate. And then we really managed to reduce that problem to acceptable level.
Fantastic. Thank you for the clarification. In the meantime, Sergey also has a question.
Yeah, so you might have said it and I could have missed it because I had some technical difficulties on my side. Does the code include cell gravity?
Yes, of course. How would I calculate collapse then of a cloud into the disk and the star? Of course, and we have published this method. We developed our own method to do that. We published it in Astronomy and Astrophysics with all necessary tests, and it's second order accurate.
You know, sometimes people just look at problems with central star already present, in which case you would still have a collapse, but yeah. Okay, thank you.
Are there any further questions for Eduard? Well, this does not seem to be the case, so I think we should thank Eduard again and all the speakers of today. Thank you very much. So the talks will be made publicly available on the COST website. I don't know the exact time scale, hopefully soon. So thank you all for sharing your knowledge and your codes. I certainly learned a lot, and I hope this will be also helpful for many more people within the COST action and maybe even beyond.